Good afternoon, everybody. This is Karen Murphy. I am the coordinator for the Western Alaska Landscape Conservation Cooperative, and it's one of many that have worked to pool funding to join with USGS to get the LiDAR elevation data that we're going to be talking about today. Just logistics things, would everybody please mute your phone while Mike is speaking, and then during question and answers, go ahead and take it off. It'll cut down on the chatter. We are going to be recording this webinar, so it'll be available for others to see in the future. And with that, let's get started. I'm going to introduce Mike Meiser. Mike is the. Can somebody please mute your phone? So I guess maybe we should wait just a moment longer. Right up here.
And Mike, if you'd like to take over screen sharing, you can bring it to yourself.
Okay, everyone, let's get started again. And this is Karen Murphy. I request that everybody please mute your phones so that we can hear Mike clearly. Mike Meiser is our speaker today for this webinar, talking about the LiDAR data collection effort that has just been completed, and the elevation data is being moved to hard drives to get distributed to funding partners here very soon, and will be publicly available sometime in September. And Mike is the project coordinator for Woolpert consulting firm, who and Mike is in charge of dealing with the grants and LiDAR acquisition projects that go to USGS's 3-depth program. And USGS was through that program, they matched the funding that 6 different agencies pulled together in order to make this data acquisition a reality. So special thanks to all of them. And with that, I'm going to turn it over to you, Mike.
Thank you, Karen, and thanks for everybody for joining here. This is a really neat project, and we're all very proud of it. It was one of the most interesting and unique and honestly difficult collections and processing projects that we've worked on here with Woolpert. So basically today what I want to do is just talk to you about this region in Alaska, which I'm sure many of you understand and know. It's called the Kuskokwim Delta in Alaska, and it's an area that's threatened by frequent storm surge and inundation, and it's coupled with extremely low and flat topography and proximity to the Bering Sea, which is basically leads to a lot of inundation and flooding and subsidence and permafrost melt and erosion and all kinds of issues out in this area. So today what I'm going to do is basically discuss the LiDAR data collection that we did over in the Kuskokwim Delta, Alaska. Can everybody see my screen okay? Or Karen, do you want to maybe respond?
Yes, we can see it fine.
Okay. You can see it without the notes page, right? I got a notes page on my screen with just a bunch of jibber-jabber that just kind of helps me along here.
Yeah, we're just seeing the slide.
Okay, sounds good. As Karen said, my name is Mike Meiser. I'm a project manager with Woolpert, and we are an architecture, engineering, and geospatial firm headquartered in Dayton, Ohio, which is where I'm speaking from today. And we have offices across the country as well. And my role with Woolpert is basically to manage our USGS GIPSY contract, which is 3DEP, which stands for 3D Elevation Program. So it's a nationwide LiDAR program through the USGS. And my job is basically to manage the task orders that come through for our USGS GIPSY contract. And this Alaska project was one of those projects. Oops, sorry. So what I'd like to do today is discuss the area of interest, and then discuss how the LiDAR will assist the region, and then talk about the acquisition itself and the processing and the challenges that we faced while doing that. And then at the end, basically I just have a quick look at some of the LiDAR and some of the communities that exist out there, and just some facts about the various communities where the LiDAR was collected. And then at the end we can have a discussion or any questions that anyone might want to ask. So the Kuskokwim River Delta in western Alaska is located on the edge of the Bering Sea, and it's one of the flattest and most vulnerable regions in Alaska. And in 2016, Woolpert was tasked by the USGS to acquire what's called QL2 LiDAR over some of the most populated and imperiled territory located within the Delta. The Delta is an extremely large area, and we did not collect LiDAR over the entire Delta, but we collected it along the western front of it. And QL2 LiDAR, basically what that means is 2 points per square meter. And I'll have some slides here shortly just to kind of give a quick overview of what QL2 LiDAR really means and how to understand what that type of density means and the accuracy that it can be. So an overview, a quick overview of what LiDAR is basically an optical remote sensing technology utilizing lasers to determine the elevation of an object or surface by using time and distance. You can see the image of the aircraft there, and it has a LiDAR sensor and a camera mounted to the bottom, and this is a common configuration. And basically what it is a scanning sensor that emits near-infrared laser pulses, and those laser pulses, the returns that come back from those, we're able to derive an X, Y, and a Z location based off of the time that it takes for it to return, and then also using GPS from a base station as well as mounted to the aircraft. The data is used in surveying mapping to capture points on the ground. It's a very common data set that can be used to create a very accurate digital elevation model, as well as a digital surface model. It can basically collect anything that's on the ground, trees, buildings, and the ground itself. It's capable of accuracies of less than 10 centimeters, and commonly it exceeds that well below 10 centimeters. And then it has the ability to fly 24/7 as long as there's no rain or clouds. You can basically fly LiDAR day or night, and as it says, it's a fast, effective method to accurately model the terrain. So when a LiDAR pulse is emitted, you get what are called returns. And depending on what is on the ground, you can get varying amounts of returns. So this is just kind of a generic example, but it shows a tree. It shows the laser pulse coming down, and then you can get your first return, which is considered your DSM or your digital surface model. And that's rooftops, treetops, and sometimes it's just open earth. Just depends on what's in the way. And then you can also get secondary returns throughout the data set, which are tree canopy, typically just a way to basically model the canopy of trees. And then typically your last or your only or sometimes your first returns are used to develop the digital elevation model. So just depending on what's on the ground, different returns can be used to create the digital elevation model. And this is just a simple illustration of first returns capturing, this is a profile of a forested area, and these are the first returns capturing the top of the canopy, and then you have your second and third capturing the understory, and then your last returns typically capturing mostly the ground, and then on the bottom just showing all the returns. So when I said QL2 LiDAR earlier, there's a couple ways to describe it. 0.7 meter nominal post spacing is one way that you'll hear it. Typically 2 points per square meter is what it means though. QL2 LiDAR is quality level 2, and that's a term that was developed in relation to the 3DEP program basically. But 2 points per square meter is what the project that we flew in Kuskokwim is, and these are actually images with the point cloud kind of sitting on top of it, so you can see the type of density that you're hitting these structures with. And you can see the rooftop on the right. You're typically getting this type of density with high accuracy XYZ elevation points that are you know, well below 10 centimeters RMSE in the case of this data set. So there were, you know, this is a USGS task order, but in addition to the many uses for this LiDAR data collection, all of these people were involved in making this project happen, and they all have their own unique reasons for the data, but all these funding partners were definitely interested in using the data for community safety and sustainability throughout the area. So what I'd like to do next is give a brief overview of why this LiDAR is important, and I'm sure there are people out in the audience here that probably know quite a bit more about this than I do, because this is something that you're heavily involved with on a regular basis. But basically, this region is vulnerable due to a constant threat of flooding, erosions, and subsidence. So airborne LiDAR is a great tool that can produce high-resolution elevation data that can be extremely useful for assessment and planning. This data will greatly assist emergency response planning, community planning, and natural resource planning. And any kind of inundation study or flooding studies in these kind of areas where you have very flat topography like this, high-accuracy elevation data is very important and very useful. So the delta itself is about 50,000 square miles plus. It's one of the largest deltaic systems in the world. It is an extremely flat area, and in many cases, the elevation barely changes within a foot for several miles. The landscape is typically wet tundra covered by large areas of discontinuous permafrost, and then thousands upon thousands of small lakes and ponds, and intertwined with a tidally influenced network of streams. And then additionally, this AOI contains the Yukon Delta National Wildlife Refuge as well. As far as the inhabitants of this region, you have it's home to approximately 25,000 residents, primarily made up of Alaskan Native tribes. Traditional subsistence lifestyle of hunting, fishing, and gathering is common, and many of these towns and villages are extremely remote with virtually no roads. So the typical transportation in these areas is river skiff, snowmobile, four-wheelers, and then anything that needs to be brought in from the outside is typically transported in by boats or by bush plane. So here are the boundaries of the project. So we did the western edge of the delta, and you can see there's a main AOI there on the left, and it contains the villages of Hooper Bay, Chivak, and Newtok. And then there's also a few satellite areas containing Scammon Bay, McCrory, and Emonic. And the area itself was about close to 1,700 square miles. It was 1,667 square miles to be exact. And we collected the QL2 LiDAR over all of those areas. So what I'd like to do now is discuss some of the primary reasons for using this data. Like I said, flat topography. This region is flat for miles inland. Minimal change can have a major impact. The typical elevations in this area range from approximately 3 to 4 meters above sea level, and inundation has exceeded beyond 30 kilometers in some areas due to low relief and the extensive network of tidally influenced water bodies. So this high-density LiDAR will be extremely valuable and beneficial to the coastal and delta terrain in understanding where water can go and doing the inundation studies. Warming temperatures are also a concern in this area. This can lead to higher sea levels, decreased natural barriers, increased storm activity, and permafrost thaw. And the regional warming may continue, and sea levels are expected to rise in coming decades, which only increases the risk to this region. Inundation and storm surge concerns. Storm surge impact is a major driver of the need for this LiDAR data. Currently, there is not sufficient data for appropriate analysis in this area, and the higher regional temperatures have degraded the sea ice protection that exists around it. And the sea ice is basically something that has helped protects from storm surge, and as the sea ice degrades, less protection from the storm surge, and again, greater concern for inundation. Additionally, permafrost thaw, subsidence, and erosion are of a concern out there. And when the permafrost thaws, it either drains into the ground or it breaches the higher ground and creates additional wetlands. Subsidence and rising sea levels are forcing some of these communities to relocate due to flooding concerns, which is in particular the case in Newtok, which is something that I'll cover a little bit later in this presentation. And then shoreline erosion is also a constant threat from storm surge, lack of sea ice protection, basically losing the land, and a better need to understand how this is happening. Another thing of importance is wildlife habitat monitoring. The Delta is home to the Yukon Delta National Wildlife Refuge, and it's one of the largest concentrations of waterfowl in the world. This data will be used to understand the waterfowl habitats and predict future movements as well. In addition, understanding the permafrost melt and where the water is draining into the streams is important because through permafrost melt, higher concentrations of minerals can empty into the streams, and it can basically change the chemistry of the water and have an impact on the fish migration patterns as well. So the LiDAR data will be utilized to better understand and protect the fish and the wildlife habitats in this area. Infrastructure and relocation planning. Assistance with settlement relocation and infrastructure planning will definitely be assisted with this data. In several cases, these settlements in the Delta have been forced to relocate due to several of the factors that I've discussed, and this LiDAR data will assist with planning on current and potentially future relocations. And then just a need for updated elevation data products. Much of the existing data in this area is very coarse and not sufficient for analysis in an area where 6 inches of elevation change is significant. Basically, older imagery products and even the IFSAR products, which are an important use in Alaska, just the resolution and the accuracy that you get from LiDAR data sets along these coastal areas will be extremely beneficial. So at one point, there actually was a LiDAR collection that occurred over the Delta. It was about 2010, I believe, and these green tiles show this area where this was collected. And as I'm told, the LiDAR data was extremely useful by the end users, and which helped push the need for an additional collection, and ultimately assisted with leading to the collection that we just did last year. So this area here that you see in these tiles, this is north of Hazen Bay, and it's approximately 15 miles north of Newtok. And then you can see it kind of against the larger AOI here. But I guess to go back just a bit, we worked with our Alaska partner, Kodiak Mapping Incorporated, who is based in Palmer, Alaska, and they are an Alaska-owned and operated company providing mapping and imagery and LiDAR services. And Kodiak, the data was collected between August 30th and October 16th, 2016. We didn't start until late August. Basically, the contracting didn't become finalized until the end of the summer of 2016. So once it did, Woolpert, the USGS, and Kodiak Mapping all worked as quickly as possible to get the acquisition started before any snow or bad weather moved into the area, which would basically prohibit us from doing our collection. So October 30th to October 16th, 2016, and they got it all completed in one season, which was great. You always want to try to get any kind of elevation data acquisition done in a single season, just due to temporal differences and things like that. So they did get it all done. They flew it with not that specific aircraft, but that's a picture of the model of the aircraft. It's a C-182 Katmai aircraft. And using a Regal LMS Q780 LiDAR sensor. And this LiDAR sensor has a rotating polygon mirror, which results in an evenly spaced point and an equally dense laser footprint on the ground. And it makes a very nice point cloud, is what they call it, on the ground that's very nicely, evenly spaced. Additionally, they collected 4-band imagery, RGB plus near-infrared with an RCD30 camera, and that data was extremely useful for us in our downstream processes. So any typical LiDAR collection, you kind of have these parameters that you have to be wary of. Typically leaf off, no snow, rivers within their channels, at or below their normal levels, and then the atmosphere has to be sufficiently clear of clouds and smoke and atmospheric haze. So actually having that was proved to be difficult in this area. We didn't have any issues with the snow, but the weather was a difficult barrier to LiDAR acquisition in this area, and shortly after we began our LiDAR acquisition, we basically were hit with about 4 massive low pressure systems over the month of September and into October. So they started in the end of August, heading into early September, but then had to take several weeks off and then resume collection and got it all completed in October. So like I said, again, excellent job on their part getting that done. As far as other challenges, I mean, just the remoteness of the AOI provides many challenges and careful planning in regards to fuel considerations and base station placement and ground survey as well. They would base their operations in Bethel, Alaska, which is one of the larger towns in the Delta, kind of the hub of the Delta. And every day they would go out and go to the various satellite towns and villages and set up their base stations within an appropriate distance to their missions for that day. So careful planning had to take place, and all of it got collected. Additionally, we worked with Kodiak Mapping to do the survey effort, and they collected what are called, there's a couple different things that you survey for when you do a LiDAR project. So you have your control data, which control is survey data that is used to process the data and make adjustments to the data, and it's used as part of the processing itself. And then they also collected the checkpoints, which are collected in the same way but not used in the processing of the data. So the checkpoints are used for independent analysis of the data to make sure that you're meeting your accuracy specifications for the project. So these pictures that you see here are actual pictures of Kodiak out in the field doing their work. The two on the left are either control or what are called NVA, which stands for non-vegetated vertical accuracy points. And basically that just means it's a bare earth, open terrain type point. So they are collecting those types of points on the open areas there. And then the person on the right is collecting what's called a VVA point, which stands for vegetated vertical accuracy. And those points are collected in the various types of vegetation throughout a project area to assess how well the laser penetrated in these areas and how well the data was collected in areas that are obviously harder to reach the ground on, like this bush here. Again, accessibility difficulties, remoteness of the area, availability of fuel and inundation wetland, or access to inundated wetlands was also a major concern. So we were able to get all this completed and use the various towns and villages throughout the project area to develop the most appropriate network of control that was possible, basically, throughout the project area. And like I said, they got all that done November 2nd through the 6th. And then also, with the assistance of several people, including Karen, we we provided community outreach documentation to the various leaders of the communities, basically to explain, you know, why we were out there, the type of work that was going to be done, how it could be helping their areas, and just as a way so people understood why there were people out there with orange vests on doing surveys out in their areas. So that was of great assistance for the people in the field as well. So when all of this data, the survey data and the LiDAR data were collected, I'm going to give a quick overview of how we process this data and the processes and steps that we take. The data, when it is collected, it is sent into the office where it goes undergoes a data QA/QC process. So basically, at this stage, you're processing your GPS to make sure that your GPS was collected properly. We go in and we check for data quality in the actual collection. So you want to make sure that there's no gaps in your data that could be caused by clouds. If you fly over a cloud when you're flying LiDAR, chances are you're going to have a hole in your data. So you have to watch out for those kind of things, gaps between flight lines, or any kind of issues that may pop up. And then if any issues come up, then you have to flag those for reflights, and you go back out and recollect those areas. So we did the data QA/QC processing, and then after all the missions have been accepted, we move into the phase that is called geometric calibration. So at this point, you take all of the data, and because this data is so dense and so large, you can't work with it as it's collected. So when you process an LAS strip, it's processed out like a flight line. These guys are out there collecting long flight lines of data, and the density of these files and the size of these files are huge. So you have to cut them into what are called tiles. So using different LiDAR processing softwares, we're able to import all of that data into basically workable sized files that are typically 1,000 meters by 1,000 meters, sometimes 1,500 meters by 1,500 meters. And once we get all that data in there, we go into this phase that's called geometric calibration. And during this portion of the process, the goal is basically to assess the relative accuracy of every flight line within any mission and make sure that every flight line is in sync with the flight line next to it. You want to make sure that they are calibrated and in line with each other, making sure that there's no variation between them or very little variation. So that consists of a lot of manual measuring, and then also some automated software that we've developed to go through and make measurements as well. And then through all those measurements, we go in and we make a bundle adjustment, is what it's called, on every mission, and then also for all the missions together. So you want to make sure every mission fits together well as well. Once all the data has been calibrated, as we call it, and then put into these tiles, then we go through and we do our accuracy assessments as well. So this is where we pull in those NVA and VVA points, and we review the data to make sure that it's meeting the accuracy specifications of the project and make sure there's no issues with the accuracy of the data. And then once we get to that, we get into the LiDAR classification portion of it. And LiDAR classification is kind of how the DEM is made. So you collect all this LiDAR, and it's in a point cloud. But when you go in and classify these points, then you can actually start to get some usable information out of the data beyond just having elevation points for everything that you collected. So what LiDAR classification is it's a primarily automated filtering routine that we run with our LiDAR processing software that goes in and basically determines if something's a ground point or a non-ground point. But basically, once you've done that, all of that data has to be reviewed because like any process that you run, you can program something to look for ground and non-ground, but it still takes people to kind of go in and look at it and make sure that the data is topographically accurate, to make sure that the classifications were done properly, and any kind of automated filtering routine like that always requires people to look at the data. So all that data is reviewed by a QA/QC staff who goes through and makes manual edits if necessary to the data and just make sure, like I said, that the data is topographically accurate and that everything makes sense and is classified properly. And then there's another thing that we do called hydro feature extraction, and with hydro feature extraction, which is a USGS requirement, we have to delineate all of the water bodies of a certain size. And when we first were approached with this task order from the USGS, we receive a KMZ, and the first thing that we always do is we kind of go in and we look at the project area and assess all these different types of products that we have to make. So as for the hydro, when we first looked at it, our first thought was, what is this? This is the most extreme network of hydro that we've ever seen, and what does this remind us of? And our first thought was it looked like the surface of the moon, and it was extremely pockmarked and cratered, and unlike any type of hydrologic feature extraction situation that we'd had encountered in the past. And we knew that we were going to have to develop some additional methods for collection of our hydro features. So on a 3-depth USGS project, we are required to collect any lake that is 2 acres or greater, and then any stream that is 100 feet wider or greater. And when we're working in the lower 48, it takes work and effort, of course, but nothing typically like what you would see in this area. And then typically the work that we do in the lower 48 is compiled by people. So you have GIS compilation staff, people going through and delineating these hydro water bodies based off of intensity, which is, these images you see here are actually called intensity images, and that's a measure of the reflectivity of the surface as collected by the laser. And it kind of looks like a black and white ortho photo. So we have people who go through and manually digitize these types of features in our standard USGS projects. But in the case of this one, that would have been extremely time and cost prohibitive to have anyone go through, and I don't think anyone would want to sit there and try to hand draw all of this. It's just an extreme situation. So we worked with the USGS, and we developed a threshold-based object-oriented extraction process to go in and collect this data. So, just like I said, with the classification, you can make a program to do these things, but you need people to review this data. So using the LiDAR intensity, the DEM, the RGB, near-infrared imagery, we were able to collect primarily all of the water that existed out there, but we needed people to go in and make sure that it makes sense, make sure that the features were collected properly, and that there were no issues with the way that they were collected or how they were connected. And it's quite a bit of work to go through and try to make sense of this entire network of hydro features. So we actually spent quite a lot of time going through and reviewing this data, but in the end, it still went much more smoothly than it would have if we wouldn't have had the feature extraction process in place. So these products are all being basically completed right now, and the work is actually done. They're just in review. There's a process that we go through with the USGS. They have what's called the NGTOC, or the National Geospatial Technical Operations Center, and their job is to take any USGS 3-depth LiDAR project that has been collected and processed by a contractor, and they go through and do a review of that data to make sure that it meets the project specifications. So all of the products are completed. Among these products, there will be classified LAS data tiles. There will be raw swath is what it's called, which is basically adjusted, calibrated swath data that's unclassified, kind of just the unclassified point cloud. There will be a hydro-flattened digital elevation model, which is in a gridded format, IMG grids, and the associated break lines that go with those as well. You'll also get the intensity imagery all tiled out the same way as the classified LAS and the DEMS. And then all of the associated metadata and reports that will be included as well. And all this data will be available in a couple different locations, and I'll have those available at the end. And I'm also going to save this PowerPoint out as a PDF and send it out to everybody who's on this call as well, so you can have it there as well. But it'll be available through the state of Alaska and on the USGS National Map Viewer as well. So here at the end, I just kind of wanted to go and I put together some slides just to kind of show off how the data looks. And in a lot of these cases, you'll actually, just to kind of explain, that there on the left, that is a LiDAR image, and that image is colored by elevation. So all the various different types of LiDAR processing software that we use, there's multiple ways to display your elevation data, and I'm sure that many of you have seen this or work with this kind of stuff too. But basically, anything that you see like that is just it's a software-specific color ramp, basically associated to elevation. So there's nothing specific that it means other than that. But anyways, I put together some images of LiDAR from the various towns. This is Chivak, Alaska, located 15 miles east off the Bering Sea, home to approximately 1,000 people, relying primarily on subsistence survival. And due to inundation along the Kuskokwim River, the original town of Old Chivak was abandoned before 1950 for a safer location. And this is something that is happening now in other areas, and it's a common theme in this area. This is Scammon Bay. This area is frequently under duress from flooding. As recently as September of last year, severe weather brought sweeping floods into Scammon Bay, displacing a large portion of the population, destroying infrastructure, access to clean water, and subsistence food stores. And this here is just another, this is an actual triangulated surface model made from that data from this most recent collection. This is McCrory, Alaska, and I apologize if I am mispronouncing any of these. If I am, I've been mispronouncing them for a while. But this is McCrory Village, located on Nunivak Island, and approximately 200 people living on this island. It's been inhabited for more than 2,000 years, and in addition to the common theme of store and surge assessment, the data here will be used to develop best placement for road and trail networks. This is Hooper Bay. Flooding may lead to relocation of this city as well, based off erosion and damage to the protective natural barriers and erosion caused by frequent storms in this area. And then this is Newtok, and Newtok is actually a community that is in the midst of relocation, and it's a village of approximately 300 people, and subsidence, erosion, and melting permafrost due to rising temperatures is forcing this community to begin relocation efforts to a new location called Murtarvik. And such a move provides many things to consider as far as infrastructure, runways, and emergency response plans. So the LiDAR will be hopefully of great assistance in that effort. And this is kind of a crude illustration, but over time this kind of shows how much Newtok has been losing as far as land, from the 50s, the 80s, the 90s, the early 2000s. The gray is basically land that has been lost to water. And then up through 2007, and then this is actually from the collection 1 year ago, and this is closer to the edge of the runway here than it is in 2007. So it continues to be encroached upon by the water, and at some point I believe it's expected to be underwater. So the town is in the midst of relocation to Mertarvik, which is basically southeast of Newtok. And then there's some LiDAR from the new collective, basically what they've gotten started as of a year ago. So like I said, schedule-wise, all the processing and deliverables from Woolpert are completed, and the LiDAR project is in final review with the USGS. Basically, we have all of the drives ready to copy the final data to and send out to the stakeholders, and then I can't say exactly what the schedule will be. The USGS would have to verify, but basically I would expect that later this summer, early this fall, they should have that data available on the USGS National Map Viewer, and then the data will also be posted following USGS acceptance on the State of Alaska's website at the address that you see there. And again, I'll send this out as a PDF to everyone so you have this as well. So final thoughts, airborne LiDAR is a fantastic resource, and it's a known resource for inundation studies and understanding where water is going to go. In an area like this, very little elevation change, it's going to be extremely useful. Storm surge and inundation research, emergency response planning, wildlife conservation, community planning, relocation planning in some cases, and a source of improved elevation. So I appreciate everybody listening in. My name is Mike Meiser again, project manager with Woolpert. Here's my email, my phone number. Basically, and I know that we're going to have some further discussion, I think, here in a minute, but I personally have just become very interested in this project just from working so much with it over the last year, and I presented this, a similar presentation to this at ILMF, which is the International Laser or LiDAR Mapping Forum. It's held in Denver every winter. And basically, you know, any kind of work that is done on this or any updates or examples of how this data has helped, if you ever want to email me or call me or let me know, I'd be very interested to hear, and at some point I'd like to maybe follow up on another presentation.